In lecture 10, we will have this introduction to binomial option pricing. This is one of the two option pricing methods that we are going to see. The other one is the Black-Scholes formula, and we will look at it later on in this course. The binomial option pricing model can help us to determine the price of an option. As we have used the idea to price other derivatives before, this model also builds the pricing result based on the non-arbitrage condition. So it's a simple no-arbitrage pricing model. This model assumes that the price of the underlying asset follows a binomial distribution. It's actually even can be simply said as the asset price in each period can move only up or down by a specified amount. In our numerical example, we will see how it works. And what it really says is just, we know that for the stock price, for example, it can move up or down by infinite amount over a period of time. The price fluctuates. That's what we know. However, in our model, we have an oversimplified situation. This assumption is extreme. It just says that for every period, your underlying asset can go up or down. Just two future ending prices possible. Only two possible. One is going up or the other going down. Obviously, the up price will be higher than the current price. The down price will be lower than the current price. But that's the basic assumption. It's very simple and seems too simple. But it turns out this simple assumption can help us to, at least to start, understand the basic pricing of options. And then if you extend this model, right, into multi-periods, and there are many up and downs over multi-periods of time, it can actually give you the Black-Scholes formula. And this idea, right, the binomial price idea is first used by Sharpe in a 1978 paper. And then Cox, Ross, Rubinstein extended this pricing method, make it very useful by extending from one period to multiple periods, make the multiple periods to infinite periods. And in the extreme, or say in the limit, you actually get the Black-Scholes formula. So it's not only useful to price European put or call option. You can use it to price American options. In some cases, there are so-called exotic options. You can also use the binomial pricing method. Not as the simple model as we see today, but in general, right, you have a multiple period binomial pricing model, and then you can price the exotic options. So let's look at this one period model. Okay, we start from a one period binomial tree for the underlying. The option we are considering is an European option on the stock of XYZ. It has 1 year to expire and has a $40 strike price. The underlying stock, XYZ, does not pay dividends. The current price of this stock is $41. We also have a continuous compounded risk-free interest rate at 8%. And then let's look at what XYZ will do in 1 year. As I have said, this underlying has two future 1-year prices. One is the up price, that is $60. The other is the down price, that is the $30. That's the only two prices this stock XYZ can be after 1 year. This is just the 1 year here is just a period assumption. Make it 1 year easier to talk about. And we know in reality it may not be 60 or 30, it may be 45, maybe 54, maybe 71. Right? There are many possibilities, right? Many things can happen during 1 year, but we eliminate all that possibilities. The only possibilities here are two. One is up, the stock go up to $60. The other is go down to $30. That's the assumption. That's the only thing will happen after 1 year. Only two things, right? Two things that can happen after 1 year. So that's for the underlying. Now consider two portfolios, right? The basic idea here is this. We have one portfolio per se called portfolio A, has one call option. Obviously, we are trying to price that call option. And in finance, what we do when we want to price some financial asset, we construct a portfolio that can replicate that particular asset's payoff. Okay, that's exactly what we do in finance. Once we can replicate the payoff, the replicating portfolio's cost, right? How much you have to pay for that portfolio that can replicating the payoff to the financial asset that you are interested. That cost for that portfolio will be the price of your financial asset. Here in portfolio A, we have our target, which is one call option, and in portfolio B, we have this replicating portfolio, right? We are replicating the payoff to the call option, and the cost of that replicating portfolio B will be the call price. And let's look at here, we actually spelled out the composition of that replicating portfolio. So what do we do in portfolio B? We buy 2/3 shares of XYZ, okay? 2/3 shares of the underlying asset, and we borrow a debt of $18.46 at the risk-free rate. So again, what do we have done? We do not buy the whole share. We buy a portion of that shares of the underlying. And then we borrow a certain amount of money at the risk-free rate. The cost for portfolio A is the call premium. That's the number we would like to know. But portfolio B has a very explicit cost, right? 2/3 of a share is 2/3 of $41. $41 is the current underlying price, right, for stock XYZ. And then because we borrowed $18.46, right, that borrowed amount of money can actually sort of help to pay. What's left, right, is $8.87. This $8.87 is what you have to take out of your own pocket. In other words, it's the equity portion of this portfolio. Right? Basically, what we need is 2/3 of one share, 2/3 of $41. we can borrow $18.46. That pays part of the 2/3 of one share. And then the rest will be $8.87. This one we have to put up for our own money. Okay. So if you think about this 2/3 of one share is your asset, then this asset is financed by $8.87 equity and a $18.46 debt. Okay, that's where this portfolio comes from. Okay, now let's look at the payoffs. Remember, for the replicating portfolio, the goal is to replicate the payoffs of the financial asset that we are interested to pricing. So for portfolio A, let's look at the payoff. We know it's the call payoff. In the upstate, your underlying price is $60, and the strike is $40 in the call, so the payoff is $20. In the downstate, the underlying price $30 at the expiration 1 year later. Strike is 40, you do not exercise the call. It's out of money, so payoff is 0. Now look at portfolio B. What do we have? In the upstate, we have 2/3 of the $60, right? You have $41 for the underlying price, and 1 year later in the upstate, it's $60. So 2/3 of $60 is $40. And then the $18.46 continuously compounded at 8%, you will get $20 out of it. So what do we have in payoff for portfolio B in the upstate is $40 minus $20. You got $20 payoff. Well, in the downstate, the underlying price is $30, and we have 2/3 of a share, so that's $20. Again, the continuously compounded $18.46 at 8% give you $20. And now, reduce the $20 by $20, you get 0. So the payoff for portfolio B in downstate is 0. Now what do we know, right? In upstate, portfolio A and portfolio B both have payoff of $20. In the downstate, portfolio A and portfolio B both have payoff as 0. And remember, it cost us $8.87 to set up portfolio B because we borrowed the rest at $18.46, right, for 8%. Then, what does that say about our call premium, right? For the call option, you pay the premium. For portfolio B, you pay $8.87. And then, in either upstate or downstate, these two financial assets, one is just a call option, the other is a portfolio, these two assets have the same payoff. So we can conclude the call premium should be $8.87. And that's the result of law of one price. We can see there is a way to create a payoff to a call by buying shares and borrowing. And portfolio B then is a synthetic call. And portfolio B is a leveraged portfolio, right? We have the equity in it and we borrow the rest, set up this portfolio, give you a call payoff. So we can also see that a call option itself is a leveraged position in the stock. And in this call, or say in this option, right, it has the risk of 2/3 shares of the underlying. The value 2/3 is the delta of this option. That is the number of shares help us to replicate the option payoff. Where these 2/3 come from, let me show you a picture. So here on the horizontal axis, we have the stock price. The stock price can either be what we have 30 or 60. Okay, two stock price. 30 or 60. That's the binomial price, right? Just 2 points. 2 points. For the call option, right? For the call option payoff at the expiration, what do we have? It's either 0 in the down state. Now let me just mark it here. That's 0. Or in the up state, it's actually 20. Let's say this point. This point here is 20. Now, this is the basic picture. I'm going to do some drawing, and you will see some lines, and you may start to think about different underlying prices, different call payoffs, but those are illusion. We just have 2 points of expiration price for the underlying, 30 and 60. And then 2 points, the yellow dots, for the call option payoff, 0 or 20. Okay, those are the ideas. Those are the 2 things we have, the only 2 things we have. 60 or 30 for underlying price at the expiration, 0 or 20 for the call payoff. And they are linked. They're linked. But now I'm going to draw this line. So this line now link the 2 call payoffs, right? One is 30, 0. The other is this one. Let me write a bit here. It's 30, 0. That's one point. The other point is 60, 20. Right? The vertical distance is 20. The horizontal distance from 30 to 60 is 30. And the slope here is 20 over 30, which give you 2/3. Okay. Now this slope is where this delta come from. Okay, that's the payoff relationship between the call option and the underlying. That's why 2/3 of one underlying share can help us to price the call option. But what I don't want you to confused about is this line. This line doesn't say, right, when I linked 30, 0, and 60-20. When I linked it up, there's a slope, yes, but this line doesn't say the underlying price can go, from 0 to 100, somewhere between 30 and 60, and a call payoff can go from 0 to 40, maybe 35 or 36 or 21, 22. No, there's nothing like that. There are just 2 points on this plane. One is 30-0, the other is 60-20. And their relationship is this delta, 2/3. Again, this delta, right, can help us to get the correct number of shares in the underlying in order to replicate the option payoff. So since we have seen, right, it's possible to replicate and pricing the call option through a portfolio. Now let's study this portfolio. So let's say the portfolio consisting of delta shares of the stock and a dollar amount, B, that's the debt in borrowing. To start, we assume discrete risk-free rate R per period. It's non-annualized, just makes things simple. Let capital R be 1 plus R. That makes the whole derivation of the formula quite easy. And there's 0 dividend yield. We can add back dividend later on. Let U be the proportion when the stock price go up. So U times S is the stock price when price go up. Okay, when the underlying price goes up. And DS, D is the proportion that when the stock price go down, denote the expiration underlying price when the price goes down. So you have in the up state, the stock price at the expiration is US, and in the down state, the stock price at the expiration is DS. The cost of this portfolio is delta S0, right, the current price for the underlying position, plus this borrowed amount. The borrowed amount helps us to pay for the underlying position, long underlying position. And turns out, obviously, the borrowed amount will be a negative number, but here we just put a plus sign here. It doesn't indicate the position in the bond. Okay, it's just how we construct this portfolio. The payoff to this portfolio is delta times the expiration price of the underlying plus the borrowed amount compounded at the risk-free rate. So that's the expiration. That's the expiration portfolio value. Okay, delta times the expiration underlying price plus capital R times the borrowed amount. Now in the binomial tree, right, we have the two states for the expiration price of the underlying. For the call option, right, there can be a upstate call payoff and a downstate call payoff, and we do have the expiration for both. Okay, based on the call payoff formula. This is exactly ST minus the strike price, and we always take the maximum between 0 or the payoff, call payoff. So these two numbers, we can write them down, right? They are known numbers. And all we need is just their expression. For portfolio, for replicating portfolio, what we have is we want, right, this delta times U S0, that's the upstate underlying price, plus the borrowed money compounded at risk-free rate give us the payoff for the call option in the up state. And then in the down state, again, it's the delta times the down state underlying price plus the borrowed amount compounded at risk-free rate. This gives us the down state call payoff. That's what we need. So on one hand, we need to know delta and the borrowed amount to formulate our replicating portfolio. Okay, so we have two unknowns. On the other hand, we need the payoff from this replicating portfolio give us the payoff for the call option in both the up state and the down state. So we have two equations. That's two equations for two unknowns. Now, all we have to do is to solve these two equations to get our two unknowns. And then we can find the expression about the call option value or the call premium. All right. The following is just a math. I'm solving for the expression about the borrowing amount and the delta. Okay. So what's the borrowing amount we can get? We have the RB in both equations, so we get both equations give us an expression for RB. And we put that together, right? It says the call option minus delta times U times the underlying spot price equals the call option payoff in down state minus delta times D times the underlying price now, right? And then we can rearrange terms, get an expression of delta. What it says, delta is the upstate payoff minus the downstate payoff divided by, this is actually the upstate stock price minus the downstate stock price at the expiration. And if you look at this picture, this is exactly how delta is calculated, right? It's 20 minus 0, okay, 20 here minus 0. And the upstate price is 60, downstate price is 30. The distance is exactly 30, okay? 60 minus 30 is 30. So delta is 20 over 30. You get 2/3. Once you have delta, right, and we can plug delta back in either equation to get expression for the borrowed amount, B. So BR, right, we just use the first equation in the upstate, right, the payoff to the call option in the upstate minus delta times U times the spot price of the underlying. And we bring delta into this place, you get this whole expression, the underlying canceled out, and it basically says what? The borrowed amount times the risk-free rate equals the up proportion times the payoff in the down state for the call option minus the down proportion times the payoff to the call option in the up state. So this is a cross product, and take the difference between the two, okay? And the denominator is the distance between the upstate and downstate. That's the borrowed amount, compounded value, or the future value of the borrowed amount. And then obviously to get the borrowed amount, we need to discount this value. Okay. This one I'd rather just view as a mathematical result. The borrowed amount I will explain it later. When we look at a more detailed picture, we can understand its function. So now we can have this call option priced because we know the value for delta and the borrowed amount. Okay, so we know the replicating portfolio's cost at time 0. What do we do? We simply put it back. Put delta times S0 plus the borrowed amount. Put delta back, right? Delta back, and the borrowed amount back. Now delta times S0 is actually, again, S0 canceled out, and this is the borrowed amount. What we do is to put the whole two fractions together and simplify it. And then eventually we find this formula for our call option. Okay, it's just a rewrite of this sum. Okay, what do we see here? First, this call option is a present value, right? 1 over capital R, discounted value. That's no surprise. And then it's a weighted average of the two up and down payoffs. So again, you see the feature of binomial pricing formula here. Right? Once we know there are two possible prices for the underlying, the payoffs are known. The up payoff and the down payoff for the call option are known numbers. And let's look at weight. The weight is what? For the up payoff, the weight is R, right, the risk-free rate, minus the down proportion over the whole distance between up and down. That's the upstate weight. The downstate weight, down payoff weight, is the up proportion minus the risk-free rate over the whole distance between up and down proportions. So again, it's actually a cross product, if you would like, right? The down, right, R minus the down proportion times onto the upstate call payoff, and the up minus risk-free rate, right? Up proportion minus risk-free rate times the downstate call payoff. Okay, down, up, down. So again, the idea is kind of cross product. And what we can notice is that these two weights, they can sum up to 1. They are exactly sum up to 1 because the risk-free rate cancel out and you got the up-down proportion distance over the up-down proportion distance. So that's exactly 1. Now, no arbitrary condition requires the risk-free rate is right in between the down proportion and up proportion, right? If the risk-free rate is even higher than the up proportion, why should I hold this risky stock? Right? Just get the risk-free asset, give me better payoff. And if the risk-free rate is lower than the down proportion, obviously I won't hold the risk-free asset. I will just hold this stock, which certainly give me better payoff. And the risk-free asset is actually a very bad asset to hold, right? So if the risk-free rate is a reasonable value and the risky asset actually is risky, right? Give me some in the upstate good result and downstate bad result is risky asset, then the risk-free rate really fall between the up and down proportions. So as long as the risk-free rate is between D and U, the down and up proportions, what we have is these two weights between 0 and 1. They can be viewed as probability measures. Actually, they are called risk-neutral probabilities. Why risk-neutral? Because we know only risk-neutral investors, right? They use the expected value to price a financial asset. So if you look at these two probabilities, now we can just denote the upstate probability as R minus D and the downstate probability as U minus R over U minus D, right? These two probabilities, right? And for risk-neutral investor, we calculate this expected value, right? The upstate probability times the upstate payoff plus the downstate probability 1 minus P star times the downstate payoff. Okay, this is the expected payoff discounted at risk-free rate. This is exactly a risk-neutral pricing. That's why these two probabilities are called risk-neutral probabilities. And this kind of valuation is called risk-neutral valuation. Okay, we can use the same method to arrive at the conclusion of the put pricing formula. Okay, and for the put pricing formula, it's still the same. You use the upstate probability times the upstate put payoff plus the downstate probability, risk-neutral probability times the downstate put payoff. Okay, again, this is the expected put payoff at the expiration, and then discount at the risk-free rate. You will get the put premium. So we have the binomial pricing formula for the put option. So no matter whether you're pricing a call or put, in fact, any other kind of asset, as long as you can put the payoffs in the upstate and downstate here, you can get the asset price. You can think about the payoff for the stock, okay? The P star times the upstate payoff to the stock, and 1 minus P star times the downstate payoff to the stock, and you discount it, you will get S0 out. Okay, you will get the current spot price of the underlying. This kind of pricing is called risk-neutral pricing or risk-neutral valuation. It's the valuation according to an expected value. That's why it's risk-neutral. It's not risk-averse, right? You don't further discount it because it's a risky outcome. It's just the expected value is good enough as a sure payoff. That's risk-neutral. And the benefit of it is that we do not need the real probabilities anymore. Right? Once you have the risk-neutral probability, you can price the financial assets. Okay, there's no need of real probabilities. You don't need to estimate, what's the chance for the upstate to occur and what's the chance for the downstate to occur. You don't need to worry about that as long as you know the two numbers. See, why there's this magic here. You know the two numbers. What's the underlying price in the upstate and what's the underlying price in the downstate. Once you know those two numbers, you can use the risk-neutral probability to price basically any asset kind of related to this pair of payoffs. Now, this is the more complete picture I've talked about for the call option, right? Point D is the upstate price and upstate payoff. Point E is the downstate underlying price and the downstate call option payoff. This so-called straight line AED, right? What it's telling you is basically, well, the call payoff, right? The call payoff can be replicated using certain amount of the underlying delta times the underlying price plus RB here. RB here is a intercept. It's actually the amount that you borrow, the future amount that you're borrowing, right? And we see this intercept is a negative number, so we are actually borrowing money at time 0. So what it does is this. We know that in this picture, right, if you have 2/3 of the underlying, basically you will have a parallel line like that. Okay, so if let's say the underlying stock price is 0, you'll have a payoff of 0. This is only saying this line here is delta times S0. Okay, and what it give you if you have $30 in the underlying expiration price, you got 2/3 of that, which is $20. If you have $60 at the expiration, you will have $40. Okay, you will have $40. So this here's actually that 20, and then here is 40. That's a non-leveraged proportion of 2/3, right, of the long underlying. It has a distance from the call payoff, right? The payoff fall above the call option here, the 2 yellow dots. So we actually need to bring it down. How to bring this asset value down? We borrow money, put a liability onto your asset value, and bring the whole payoff down to 0, 0 at this first yellow dot, and 20. So basically we know, right, what you need is a future value of $20. So that $18.46, several slides before, right, $18.46, it's just the present value of $20, right? Can bring your payoff on the 2/3 of a share down to the level of the payoff of that call option. That's what it does. That's what the borrowed amount does in this portfolio. Okay. Now this is the picture for the put option. This is the picture for the put option. You still have the up and down. There's the downstate payoff for the put option, and in the upstate, we assume the put option because the strike price is between the upstate underlying expiration price and downstate underlying expiration price. Right? This is the upstate underlying expiration price. This is the downstate underlying expiration price. The strike price is right in the middle, and what we have is in the down state, you have X minus the down state expiration price. In the up state, right, the payoff to the put is 0. So again, we have the 2 points, E and D. And linked it up, we have this kind of replicating portfolio for the put option. And it actually lending out this intercept is positive. The RB here is actually positive. What it does is you actually lend out the money, right? To replicate this put option, you have a negative slope, right? This slope is negative, so you actually sell the underlying share and lend out part of the proceeds. In that way, you sort of lock in a certain portion of the strike price can be paid back, right? When you're lending out money at time 0, you'll receive money back at time t. So it's money back, right? In that way, if you think about the shorted share, right? Delta S0, that's the shorted shares you have at time 0. In the at time t, at the expiration, the shorted position will be a liability. Right? It will fall below 0. That's the liability. You shorted it. And then the money lending out will move that liability upwards to the payoff for the puts. Okay, that's how it works for the put option. When you in the underlying position, remember the put is a short exposure. To get a short exposure, basically we are selling the underlying shares. And then we need to adjust that liability. It's fall below 0. Okay, we need to adjust that liability up to give us the put option. So we actually need to lend out certain amount of money, this B here, in order to achieve that adjustment to replicate the put payoffs.